Okay, here we have the notes for section 6, which is the counting. So we've got permutations and combinations, whether or not order counts. So permutations are arrangements in which different sequences of the same item are counted separately. So if you have the letters A, B, and C, there are 1, 2, 3, 4, 5, 6 different ways with which you can arrange the letters. Combinations are which order doesn't matter. So with the letters A, B, C, these arrangements are all the same letter. So for a permutation, order matters. For a combination, order doesn't. So if you think about a combination, if I just need to select 3 students to run an errand, that's a combination. If each errand is different, then it's a permutation, because who I pick first has a different errand than who I pick second, than who I pick third. Okay, some notations. You have this factorial symbol, the exclamation point, denotes the product of decreasing positive whole numbers. For example, 4 factorial is 4 times 3 times 2 times 1. 0 factorial is defined to be 1, even though it's not technically a positive number. So down here we've got counting rules. So you have the fundamental counting rule. So m times n is the number of ways 2 events can occur, given the first event can occur m ways and the second event can occur n ways. So a lot of times you see this in like the number of pizzas you can make. So if there's 3 different sizes and 4 different toppings, you're making a 1 topping pizza. 3 times 4 is 12. There's 12 different pizzas, small, medium, large, for each of the 4 toppings. So a factorial rule. Permutations of n different items, when you select all n of them, is n factorial. So if I have 6 kids to run 6 errands, there are 6 factorial ways in which I can select them to run the errands. Okay, got a couple more rules up here. So permutation rules when all the items are different. So n is the total number of items. R is the number you're selecting at a time. So it's n factorial divided by the difference factorial. When some items are identical to each other, it's n factorial, and then n1, n2, so on and so forth, are the number of repeats. So a lot of times you see this in how many different ways can you arrange the letters in the word banana. So because some letters repeat, there's 3 A's, 2 N's, so it could be B, A, N, A, N, A. So that's 6 letters, so 6 factorial on top. Then you have a 3 factorial for the repeating 3 A's and a 2 factorial for the repeating 2 N's. Combination rule, so order doesn't matter. N is still the number of items total, R is the number you're selecting, so it's n factorial, and on the bottom you have the difference, and then how many you're picking at a time. So the permutations does not have that r factorial, whereas combinations do. Okay, so example 1 says computers are typically designed so that the most basic unit of information is a bit, which represents either a 0 or 1. Letters, digits, and punctuation symbols are represented by a byte, which is a sequence of 8 bits in a particular order. Then it gives you the letter A is this pattern, the number 7 is this pattern, so it says how many different characters are possible. They're all represented as bytes. So essentially you have 8 positions and you have 2 values for each position. So 4, 5, 6, 7, and 8. So 8 different values, which is the same thing as 2 to the 8th, which is 256. So if you use 8 bits, you can code 256 different characters. Okay, so number 2, history pop quiz has one question which the students are asked to arrange the following in chronological order: Hayes, Taft, Polk, Taylor, Grant, and Pierce. If you make a random guess, what's the probability of selecting the correct order? So we need to figure out how many different ways you can pick them first. So there are 1, 2, 3, 4, 5, 6 presidents. So randomly guessing the first president, you have 6 options. Randomly guessing the second, you now have 5 because you already used one of them up, and so on and so forth. 3, 2, and finally you have only 1 president left to pick. So this is the same thing as 6 factorial. So mathematically, 6 times 5 times 4 times 3 times 2 times 1 is 720. So there are 720 different ways with which you can arrange those names, which means the probability of selecting the correct order, there's only one correct order, is 1 out of 720. So if you want the decimal, I don't know, it's probably some goofy number. Yep, equals about 0.00139. So less than a 1% chance of guessing correctly. All All right, so example 3, in horse racing, a bet on an exacta is a race won by correctly selecting the horses that finish first and second, and in that order. So you can't just say, these 2 horses are going to finish first and second. You're going to say, this horse is going to finish first, this horse is going to finish second. So you have 20 horses total. So that should probably be BETTOR. Randomly selects 2 of these horses for an exacta bet. What's the probability of winning by selecting Super Saver to win and Icebox to finish second, which they actually did, and do all of them have the exact same chance of winning? So to do this, there are 20 horses available. So we need to figure out how many different ways we can arrange them when order does matter. So this is a permutation. There are 20 horses total. We need to select 2 of them. So for a permutation, that's n factorial divided by the difference factorial. So this comes out to be, let's see here, divided by 18 factorial, 380. So there are 380 different ways I can pick 2 horses to finish first and second, which means the probability is 1 out of 380. So now the second part here where it says do all the different possible exacta bets have the same chance of winning, that's actually no, because horses are different. Some run faster than others, so some are more likely to win than others. So you can't necessarily say that every possible combination has the exact same odds. Otherwise, when you went to bet, they'd all be the exact same. Okay, example 4. So when you get a telephone survey or something like that, in order to check for people not necessarily answering honestly, you give different subjects rearrangements of the questions so the order does not have an effect, and check individual subjects by repeating a question with some rewording to see if the answers are consistent. So in one particular survey with 10 questions, 2 of them are the same and the other 3 are identical. So you have 10 total questions, 2 of those are a repeat, 3 of them are also a repeat. Like questions 1 and 2 are the same question, and the questions 3, 4, 5 are also the same question, but different from 1 and 2. For the survey, how many different arrangements are possible, blah, blah, blah. So this is repeating events. So it's the total number of options. So there's 10 questions total. 2 of them are identical. A different set of 3 are identical. So 10 factorial. Your calculators have factorial buttons, which makes this math much easier. So there are 302,400 different possible arrangements of questions. Is a practical survey enough subjects so that every possible arrangement? So no, not practical. That's way too many people to have to call. Most surveys only survey about 1,000 people. Okay, example 5, Max 6 Lotto, winning the jackpot requires that you select 6 different numbers from 1 to 49. The same 6 numbers must be drawn in the lottery. Drawn in any order, so order does not make a difference. Find the probability of winning a jackpot when, excuse me, when 1 ticket is purchased. So there are, from 1 to 49, there are 49 different numbers. So this is a combination problem. So 49, combination, I need to choose 6 of them. So for a combination, it's 49 factorial over the difference, 43 factorial, times how many you're picking, factorial. And this, let's see if my calculator can handle it, 49 factorial divided by 43 factorial divided by 6 factorial. Let's see here, 139838816. So there are 13,983,816 different lottery ticket combinations. So find the probability. Well, only 1 ticket's going to win, or 1 combination. More than 1 person can have the same number, but only 1 combination wins. So that's the probability of winning if you purchase 1 ticket. So this is why lottery, not a good investment. You have a vanishingly small chance of actually winning. All right, and the last one here, 6. So a corporation must appoint a president, chief executive officer, and a chief operating officer. So 1, 2, 3 different officers, planning committee with 3 different members. There are 8 qualified candidates, and officers can also serve on the committee. So how many different ways can the officers be appointed? So this is a permutation for the officers because the jobs are different. There's 8 total, and I select 3 of them in a permutation. So permutations are the total divided by the difference. So 8 factorial, divided by 5 factorial, there are 336 different combinations of officers. For the committee, order doesn't matter, so because you just need 3 different members, so that's a combination. So combinations are the total. On the bottom you have the difference and the number you are selecting. So on a combination, these 2 numbers should always add up to that number. So to see our previous answer, do one extra division step. So there are 56 different ways to select. So like here in a combination, if I select person A, B, C, so 6, 7, so say, you have these people, I'm selecting 3 of them at random. But for a combination, ABC is exactly equivalent as BAC, which is the same as, CAB, because it's just 3 people on the committee. So these, as far as combinations are concerned, are identical. I just need 3 people. These are the same set of 3 people. Now for up here, if you have officers, president, CEO, COO is different than president, CEO, COO. So for combination, these 3 things are all different because A, B, and C each do a different job, whether they're first, second, or third. So that's kind of illustrating the difference between a combination and a permutation. But that brings us to the end of this section.